Well, good evening, everyone. It is 6 p.m. Eastern Standard Time. I'm Charles Schultz, and this is the Randomizer for the 8th of March, 2022. And tonight's term is going to be solid state. So that term has a lot of uses, and we'll talk about the obvious one first, and then we'll go to the other one. I'm going to also suggest that if you have an Oculus or a Vive or any other 3D headset, go to schultzlaboratories.com or universesciencecenter.com, walk around our galleries, explore a little, and see some of the things we're adding. All of our new exhibits are going to be more amazing, more interactive content. Invite some friends, show it around, get some people to sign up, join, and become members. And also enjoy the Randomizer 6 p.m. weeknights, Eastern Standard Time, and 9 p.m. weeknight on Mondays only at this time. We'll be doing our lessons and our classes. So we've got some new material coming up very soon. We're going to take a 2-week hiatus while we do some changes in our studio here and add some other material. So everybody, please join us, and it's going to be a lot of fun. And welcome to everybody who's watching the Randomizer. So tonight, solid state. Now, obviously, the first thing you would think of if you didn't know much about electronics, solid state would be one of the states of matter. And matter, of course, as we know, exists in numerous states: gas, liquid, solid, plasma, and there are a couple other exotic states as well. But they're not something you're liable to run across or see, or certainly not touch. Solid is, of course, when all the atoms in a material are joined together in an immobile manner, like a bar of steel or a block of wood. And on the other hand, some solids are joined together, but they're flexible, like a sheet of rubber or some silicone or something. But the solid state that really is of interest here is that used in semiconductors and electronics. Semiconductors have become an absolutely pervasive part of our world, and they have a very long and interesting history. So obviously, some people are clearly familiar with the fact that before we had microchips, we had individual little pieces of silicon fabricated into transistors and diodes. And these little chips of silicon are made by the thousands with a photographic sort of process on a wafer. So the way it starts out is that you start with a wafer of pure crystallized silicon in most cases, and you project a light image, thousands of copies of the device you want to make onto that wafer. But the wafer is coated with something called a photoresist. And it's the same material that you'd use to make a photograph in a sense. Light can sensitize or harden the material, and darkness will leave it untouched. After exposure, you wash it with a developer, and part of the material remains behind, and part of it washes away. And so where the presence of light was determines this. Now, some is negative photoresist and some is positive photoresist. So some will stay put in the areas the light hit and wash away where it didn't. Others will stay put where the light did not hit and wash away where it did. And you choose the one you need for the application you have at hand. But after that's done, there are holes in the mask, and chemistry is used to diffuse materials in. It might be a very high temperature furnace. Oxygen might go on it, silicon, metallization, different materials, and it makes the semiconductors in the wafer of silicon by literally bleeding into the wafer. It's called diffusion or epitaxy. When it's done, then you take a diamond wheel and you slice it up in so many directions, and it fractures into thousands or millions of little dice, tiny pinhead-sized bits of semiconductor that represent individual devices such as transistors, photosensors, or resistors in some cases, but normally not a resistor, rectifiers, diodes. So all these components can be made on a wafer all at once. But the question is, how did we reach the state where we use solid-state electronics? What came before that? Well, it turns out that the most popular method of doing it, and in fact the only really practical method, was vacuum tubes. Well, vacuum tubes are basically a light bulb with extra elements inside it, to be honest. The first usable vacuum tubes were simply the incandescent light. But people who experimented with it, like Lee de Forest, would add an extra filament or a plate or other things inside and experiment with the flow of electricity. And even Edison did the experimentation of this sort. And at some point, it was discovered that the flow of a signal from the filament to a collector in there could be moderated by a current charging a little plate that stood in between, called a grid. So, by applying a voltage to the grid, the voltage would control how much current flowed through the vacuum tube. And this was the first amplifier, because a very tiny voltage charge can control a significant movement of current through the vacuum tube. So amplifiers, oscillators, other devices were soon made using vacuum tubes. Now the problem with vacuum tubes, even though they're very useful, they get hot. They burn out rapidly. They use a lot of power, and they generally require a couple of 100 volts to operate. And it's not really conducive to making very tiny devices. You end up turning a thing on, waiting for it to warm up, and then being able to use it. So the other thing is with a vacuum tube, its characteristics will sometimes drift over time. So vacuum tubes were the big method of doing things before the semiconductor. So the invention of the transistor, that must have been it. Actually not. There were solid state devices before the transistor. This is an interesting thing. Rectifiers. Rectifiers are like check valves for electricity. If you know anything about plumbing or hydraulics, a check valve is basically a device that fits inside a tube, and it might have a little ball that allows the fluid to flow one way, but if it goes backwards, the ball plugs the hole and the fluid can't move backwards. So a check valve checks the flow of fluid. A diode or rectifier does exactly the same thing for electrical current. So a vacuum tube obviously can act as a rectifier because from the filament to the plate, it only moves negative to that plate, positive, at cathode to anode. But how do you do that in a solid crystal? Before vacuum tubes, semiconductors such as copper oxide or silicon carbide already existed. So what's copper oxide all about? You're going to learn an interesting trick here. You would take a plate of copper, you would clean the face, you'd attach an electrode to the back, and the front of it would get oxidized with a flame or some other controlled process until it got a black layer of copper oxide on it. Now it turns out that the junction between the metal and the oxide is a semiconductor junction, and it will only conduct in one direction. So you place a plate of copper in an oxidizing environment, the back stays clean, and then you put a fine grid of wires on the front of it. And guess what you've just made? You've made a very simple, low efficiency, but functional photovoltaic cell. So it is possible to actually make sun harvesting power systems out of copper plates oxidized on the front. The problem is they're not real efficient and they're very delicate, but it can be done, and this was done in times past. Before this, selenium was the element that was usually used to make rectifier or photovoltaic panels, I should say. But rectifiers made of copper oxide were common in old devices. If you go back to a 1960s television or 1970s early television, you will often find a stack of little squares all fastened together with a wire going in one end and out the other. That is a copper oxide rectifier. So that was a semiconductor, didn't take a vacuum tube to do. But believe it or not, there were even light-emitting diodes before that. There is a crystal made of two elements, silicon and carbon. Now, silicon and carbon are like brothers. They both have 4 electrons in their outer shell, and they're capable of joining 4 things. If you look at methane gas, it's a carbon atom with 4 hydrogens fastened on it like a tetrahedron. That's methane. If you took a silicon atom and did the same thing, put 4 hydrogens on it, it would make silane, not methane. So they have some similarities in what they will do chemically. But silicon carbide is a crystal made of an order of silicon and carbon atoms stitched together into a lattice. And this has an interesting property. If you apply a voltage at a contact point, it will act as a rectifier. Believe it or not, this wasn't the first diode, but it was the first light-emitting diode. When you apply a voltage to that crystal of silicon carbide, it'll give off a very weak greenish-yellow glow. It's difficult to see, but it does actually rectify like a diode, and it does actually give off light. So it can be done, and it has been done for many ages. But there's one other kind of diode that they used to make and it was called the galena diode. Galena is an ore of lead, the metal, and galena ore was cut into small pieces, and what they called a cat's whisker, a tiny whisker of metal, was placed on the galena, and it was moved around till they got just the right connection, and it made a simple diode rectifier, and it was the basis of what they called crystal radio sets. Crystal radio basically literally had a tiny earphone, an inductor wound out of copper wire, a tuning capacitor made of mica and aluminum plates that you could move around to tune the frequency, and this cat's whisker at the heart of it. And kids had a big thrill out of making their own radio from a cat's whisker and a bit of wire and an antenna wire run across their yard. So years ago, this was a very common thing. The crystal radio set, something you may want to look up. So that's a solid state device, and it was made by hand without semiconductor factories. But solid state electronics, as we know it today, really took off when the first unijunction transistor was made by a pair called Bardeen and Cooper. Their first transistor was a unijunction. It had a single semiconductor junction, and they were able to vary the voltage passing through it, changing the resistance of the device. So this device is now on display in a museum, and if you look up first transistor, you're very likely to find some pictures of it. It doesn't look like anything like what you'd think a transistor does. It looks like a block with a couple of wires stuck to it. So, contrary though to belief that our advanced electronics technology came from captured UFO technology, as some people claim, the transistor actually was outlined in great detail in a patent in 1923, and I'll leave that as an exercise for you to look up. So, semiconductor electronics, because of their durability and the many different types of crystals, artificial crystals we can use to make them, has become the go-to method for almost every computing and electronic device on Earth. And there are thousands of billions of electronic devices floating around out there. Might be hard to believe. Look up the numbers. It's amazing. Semiconductors are everywhere. So, every computer these days, I won't say every, but 99.9 or more percent of all computing devices today are made out of either silicon or a mixture of crystals called gallium arsenide. It's a special type of crystal. And there's a reason why you would make a special crystal. It has different voltages that it will work at. Earlier semiconductors, before silicon, used an exotic material called germanium. Germanium transistors are actually quite efficient, and they have an advantage over silicon transistors, and that is silicon transistors take about 600 to 650 millivolts, 0.6 volts or so, to turn on and conduct. Germanium transistors can run as low as a quarter of a volt or less sometimes. So it is the binding of the electrons on those atoms that determines how much energy, how much voltage it takes to make the electrons flow. So solid state can refer to the state of matter, or it can refer to our electronic devices, the semiconductors themselves. Vacuum state electronics was the rule of the day until the invention of the transistor, which became so easy to make and so popular that soon it absolutely blew away the competition. So now everything is on a microchip, and there are literally anywhere from millions to a billion or more transistors in a computer microchip. So we've gotten really precise and very advanced in how deeply we can shrink the size of the components it takes to make functional electronic devices. We're now running up against something called Moore's Law. Roughly every 18 months, the rule was we could double the density of electronic devices, and this continued for many years. But as we get smaller and smaller devices, they become more sensitive to effects in the environment, even including heat or quantum noise. We're down to the point now where if the law had continued in its original trend, we'd be making transistors out of just a handful of atoms, and we're not far from that. Many of the wiring and features in some of the wafers today are only a few nanometers or billionths of a meter across. And so when somebody says, oh, this is a 5 nanometer device, 1 nanometer is about the distance of 10 hydrogen atoms in a line. A 5 nanometer device is the size of about 50 hydrogen atoms. That's how tightly we've pressed the structure of semiconductor devices on wafers and specialty devices these days. Unless something changes, we're up against a wall, and we can't make our devices any smaller, and Moore's law blows up. So, interesting things happen in the form of semiconductor advancement. We've used light to make the masks, and then the light waves were too big, and then we went to X-rays, and now we're down to high energy X-rays, and pretty soon that just isn't going to cut it, because beyond a certain point, the X-rays have enough energy that they actually can damage the wafer you're working on. Now, there's some workarounds, and they're working on it. Quantum computing, by the way, looks like it may be the go-to in the near term. We're making quantum computing, which doesn't use solid state in the traditional way. It uses super chilled materials to make quantum transitions occur in a controlled fashion. Computing with quantum systems can be thousands of times faster, if not more, than the systems we have today. So fear not, we're not going to run out of space at the bottom for a while yet. Quantum computing is going to be the next go-to, and the solid state that we know today will be morphed into something completely different. So now, if anybody has any questions about solid state, I'll be happy to entertain them and give you possibly some answers for them. And meanwhile, I encourage you to go to schultzlaboratories.com or universesciencecenter.com, see our page, sign up, become a member, join our classes, support our growth. And we want to spend a lot of time sharing our educational methods and environment with everybody on Earth. This is a great task, and I think it's one of the best things we can do. Let's make it go forward. And if there are any questions, I don't see anything popping up on the text window, and I don't see anybody waving their hand. Okay, very good. Now, quick quote before we close, and it is this one. This is a nice one. If anyone defiles the temple of God, God will destroy him, for the temple of God is holy, which temple you are. And that's from 1 Corinthians 3:17. For people who hurt people of faith, who do evil to them, it is promised that there will be destruction if they don't change their ways. I know that in this world, it's often tough for us to accept the things, the indignities that we suffer. But you know what? There is a tally of these incursions, and at the end, we will all receive our rewards. And that's something to keep in your heart. So thank you for joining us tonight. I really appreciate the randomizer and the people who come and see it and participate. Everybody have a wonderful evening, and I will be back tomorrow with a new randomly selected subject. So have a great evening and make the world a better place. And thank you.